Thank you very much. Further questions during the coffee, please. Okay. Thanks, Stefan. Okay, next talk. Antonio Politi, Hamiltonian dynamics in laser systems.
So, just a moment. Okay, you have to. Okay, so good morning to everybody. Thank you for the invitation to talk second year in a row in this conference. And so how to start? I mean, if the pleasure of doing research consists in finding unexpected and sometimes even counterintuitive behavior, I mean, that's a relatively good example, because a laser is a well-known dissipative system operating out of equilibrium. So it was really a surprise in the end to discover that a large class of lasers in the end behaves very closely to Hamiltonian, displays a nearly Hamiltonian dynamics. Obviously nearly, in spite of the fact that strong dissipations are in action. So that's just to make a short summary of the concept behind this paper. So it is important to acknowledge the collaborators, because this is not work of mine. One is a long-term friend, Giacomelli in Florence. And the second collaborator is Serhii Yanchuk, currently at the Climate Institute in Berlin. He's moving to Cork in Ireland. Okay, so that's the outline. Essentially, another way to briefly summarize the content of this seminar is say this is a crash course in nonlinear dynamics, because I'm going to start with the model, and to arrive at the end, I will meet and cross questions like adiabatic elimination, dissipative dynamics, systems with delay, spatiotemporal dynamics, even if you want synchronization at some level. So it's a good test for a student that is learning nonlinear dynamics. So the starting point is the Arecchi-Bonifacio model. Is essentially the most general and I would say first principle model developed 58 years ago to describe longitudinal instabilities in lasers. I mean, maybe you have encountered the name often Maxwell block, but if one goes and checks the literature, it would be more appropriate to attribute this model to Arecchi and Bonifacio. They published this in 1965, before anybody else. So this is the starting model. I will show you briefly the equations and what to do. And I am going to simplify by proposing a sort of, an expansion in Legendre polynomial. What is the motivation for doing that? Is to remove the spatial dependence. And then truncation. Truncation is a type of Galerkin truncation. Is anomalous because this set of equations are still complicated because they are delayed equations. So yeah, I'm going to remove the space dependence, but the delay is still there. So the model is still complicated and keeps the complexity of the original model. And so far, it's, say, the first part of the story is over. Then I'm going to focus on a not so special subclass of systems, those where the ratio between two decay rates that are encountered in fiber laser and semiconductor laser. So most of the lasers that people are dealing with now is characterized by a very small or very large, depending on the way you work, parameter, and is suggestive of the adiabatic possibility to eliminate adiabatically a variable. Which one? That's an issue, because the straightforward idea doesn't work and one has to proceed differently. Once you have done that, you will discover that the model, the delayed model, can be recast in a form which is space-time, where the space is no longer the original space, it's another formal space. And this model here is the one that I will tell you has a Hamiltonian structure. Obviously, this is the zero-order model. The model cannot be Hamiltonian, strictly speaking, so you have to add the correction terms. And once you equip this Hamiltonian model with suitable small correction terms, we arrive at the final model, which we have tested, works nicely, and is able to reproduce the Arecchi-Bonifacio model in the very beginning. So that's a really long journey. I mean, I have a lot, too many probably slides, but I want to focus on the steps, on the conceptual steps, not on the math. So the model is this one, and this is, okay, the model is this, is a partial differential equation. So there is a space here, F is the field, electric field, P and D are the atomic polarization, population inversion, and there is also hidden the delay, because in practice, what you need is to close the equation in the following way. You need to say to the model that the field getting out here is reflected and after some time is re-injected here. This introduces an additional complication, which is precisely reported here. So this is a system with two sources of infinite dimensionality in phase space. One is the spatial dependence, and the other, sorry, here, and the other is the delay. So the idea, the first idea we had was to rewrite this model in a moving frame, because you see that this term here is just convective. It's telling you that according to this, there is a profile which moves with velocity 1 in these rescaled units. So why not using a moving frame, a frame which moves in these scales with velocity 1, which means in reality with the speed of light. And that's what you get here. Is an equation where in practice the time dependence is only up. Initially noticed and made somehow rigorous was that the spatial dependence of the field here in this moving frame is very weak. Even when the laser is operating in a highly nonlinear regime, if you want to look at any time at the profile of the field from the beginning to the end of the cavity, you discover that it's always very weak. So I'm going to jump okay, sorry, what's going on? Okay, so I mean, I'm skipping some slides. I just want to go, okay, here, no. Where should I? No. Oh, this one in the, okay, here, for lucky. So here what I am reporting is in suitable units, the cavity, the active medium is a rescale from -1 to 1, is the field profile in 3 different moments when a series of pulses is being generated. So you see that the field profile is rather smooth, I mean, doesn't contain any complexity. So the idea we had was, why don't we expand this spatial dependence? Obviously not in Fourier modes, because there is no periodicity here. So we decided to expand in Legendre polynomial. It's an orthogonal basis. And it turns out that if you use an expansion in the Legendre polynomial, you already get a very nice, accurate model if you stop at the first order, meaning that you approximate these curves with just a straight line. By the way, these curves have been obtained in a regime which is super nonlinear. We have tried to be as nasty as possible. Okay, so we have decided to truncate the model. Okay, just okay. Those. Let's. Okay, I mean, I'm just jumping to. There is something which I don't know what's going on. Where is the model? There's some delay, which maybe is okay. Finally, I got it. So the model, you can just look at these equations here. So you see the space dependence has disappeared. I'm only considering the first mode for the polarization, for the atomic inversion. And here, there is this equation which is telling you how to express the field at the end of the cavity as a function of the field at the beginning of the cavity. I mean, in practice, this is the source of the delay which is still present and makes the model absolutely non-trivial. Okay, so okay, let's forget about this. Let's go to the ring laser and this model that I have just flashed, just to show you that it works. I'm comparing the second laser threshold. What is the second laser threshold? It's the threshold when the laser the field starts oscillating. And so here is this parameter gamma, which is the ratio between the decay rate of polarization and population of population and polarization. And the red curve is the analytical curves that you obtain solving the original Arricchi-Bonifacio model. These dots are the points obtained numerically by finding the threshold in our simplified model. So, and in spite of the fact that we are covering 2 decades here, the agreement is fairly nice. So, as a confirmation that we are on the right track. So, okay, first simplification has been made. So now how to proceed? That's the second part of the story. And to be mathematically, say, rigorous, there is an additional, say, simplification. From now on, I'm dealing with the resonant case. So I'm assuming the laser is perfectly resonant with the cavity. And I also assume that the reflectivity is close to 1, which, by the way, is what the experimentalists want to do, work with, because typically is 90% or something like that. Okay, so under this approximation, so I'm rewriting the model that I was flashing before, the one that I want to work with, and this gamma is the parameter I was anticipating in the very beginning. This number, just to give you an idea, for the ring laser is 10 to the minus 12. So that's really a very small number. And the idea that many researchers before us had was to eliminate adiabatically. Maybe this is not so transparent in this representation, but nevertheless, that's the idea, which it's quite intuitive, because the fact that this is small, it means is a consequence of the fact that the decay rate in, say, real physical units of this variable is very fast. So one is very much tempted to adiabatically eliminate this variable. But if you do that at this stage, you get equations that are unstable and absolutely unphysical behavior. So you cannot eliminate adiabatically the polarization. And this is the first hurdle. Now, what we did was, following some intuition which was present in this paper by Deval-Carcel, Prati, and others some 20 years ago, we have made a change of variables. And practically, what is important for you to catch, to understand, is that we have introduced a new variable, which is a mixture of the atomic polarization and the field. And it turns out that if we adiabatically eliminate this variable u, we get a much better model, which at least has a physical meaning and is the first step towards the discovery of the Hamiltonian dynamics. And in fact, here below you find this is exactly the same model I was starting from. So no approximation, no adiabatic elimination. I have simply introduced the new variable u, and I'm also introducing this capital gamma is the square root of the previous gamma. I have changed the scale of the time, but in this representation it's quite transparent that this equation is characterized by a very large decay rate because gamma is in the denominator, and it makes sense to eliminate this variable. And in fact, this is what I'm going to do next. And okay, these are the rescaling that I have operated. And if I eliminate adiabatically this variable u, practically it means that I replace the differential equation for u with this ordinary equation here. And by the way, this ordinary equation introduces a strange, maybe not so strange for mathematicians, delay term. Since there is the derivative, this is called mathematically a neutral delay equation, which is nasty and very little understood, or better said, very little studied. Okay, I'm also redefining the smallness parameter, it doesn't matter, I mean, what it is. And now this is the model I want to play with, where epsilon is a small parameter. So what you see here is that if in the first approximation, I assume epsilon to be 0, you see that any solution of f that is periodic of period t, any, provided only, and the only constraint is that if the average value of f square, f is the amplitude, f square is the intensity. So provided that the average over the entire period of the amplitude is equal to 1 in this scaled unit, that's a condition for having this G, which is the population inversion, not to deviate over long times, diverging, not to go into 0. So any solution which is periodic and with a very specific average intensity is a solution of this equation at this level of approximation. So there is a huge, diversity. And okay, so it's obvious that you cannot simply eliminate this epsilon. You must include it. And the fact that this behavior, this periodic behavior, is nearly accurate, the simplest idea you get is to introduce a space-time representation. The space-time representation is such that practically I take the time axis, this is the y of the time axis, I wrap around a cylinder in this way, and I transform the position along this infinitely long wire into a horizontal position, quantified by this Greek z, and a vertical position quantified by this other variable. And since I know that from one delay unit to the next, the change is very small, I can introduce treat this as a pseudo-continuous variable. That's the reason why I can now write partial differential equation with the space and time, including taking into account the derivatives. So, I mean, if I make some other change of variables which are totally irrelevant from the conceptual point of view, you discover that this model at the leading order can be written as in this form here, where S is the logarithm of the field intensity, Q is, I mean, essentially the population inversion. And what's the meaning of this model? The meaning of this model is not so transparent, but if you introduce this other change, you combine together time and space, introducing a new time and a new space, the model looks like this. The model is nothing but a nonlinear wave equation. This wave equation this is a nonlinear force which can be seen as generated by a potential, which, by the way, is a Toda-like potential. So to the zeroth order, the laser behaves like a nonlinear wave equation, but the Hamiltonian, obviously associated to this equation, can be interpreted as an energy, but has nothing to do with the energy that is pumped into the laser or absorbed. So now, since it is continuous in space, there are two conservation laws. And in the original representation, the conservation laws we call pseudo-kinetic energy. This is the first one, and you understand why it's pseudo-kinetic. I mean, it's a pseudo in a sense because sigma here is playing the role of space. It's not like time like in general. And then we have the pseudo-potential energy. Both of them are conserved. So I mean, maybe I can say stop here to leave some time for discussion. This is, I'm showing what? I'm showing that in the top part, in the two panels, I'm producing the spatio-temporal pattern generated by integrating the original delayed equation, so the laser model, if you want. And using the same initial condition here for the Hamiltonian model, I produce the pattern And you see that this pattern and this pattern obviously cannot be the same because of approximation, but nevertheless, it reproduces decently the original pattern, giving evidence that the Hamiltonian approximation is a good approximation. This is another initial condition, which is different, and in both cases, the accuracy is quite good. I mean, I don't have time to go into further detail. I only want to say that if you proceed further, you add correction terms to the Hamiltonian model, we get a model which reproduces decently the behavior of the original model, and that's it. I mean, so thank you for your patience.
Yeah, for a question? Yeah. If you, Antonio, introduce an additional order in the Legendre expansion of the field.
Sorry,
if you include the second order term in the expansion in Legendre polynomial, did you think that have again Hamiltonian like dynamics or?
If you want, you can do yourself the work. I mean, I mean, it was a nightmare to go down, say, from the original model to the Hamiltonian one, because remember that I have even eliminated the tuning, because already adding the tuning, I don't know what happens. I'm confident it should work, but anyway, I mean, adding other modes, I might say, on the one hand, I know for sure that the model is going to change only a little because the accuracy is very good. I mean, probably the Hamiltonian structure is going to be lost, but I mean, this doesn't, in my opinion, mean anything negative, because in the very end, the most relevant model, the minimal model, is not exactly Hamiltonian, because Hamiltonian means you fix the energy, the value you want, and it stays there forever. In the laser, in reality, the energy is self-determined, and it is self-determined because of the correction terms that you must include. So what could be the case is that if I go to one step beyond in the expansion of the Legendre polynomial, additional correction terms are appearing, and they might modify, say, the self-determination of the energy. That's the point. I don't think that the Hamiltonian structure at zero order is going to be lost.